This is the last episode of Season 3. All season long, we built a RAG system, an agent platform, an inference service, and vector search. 4 systems, each doing its own thing. But in front of all of them, the same thing was missing. A single unified door, one place every request passes through first. In this episode, we install that door, the LLM gateway. You might think gateway sounds fancy, but you already know it. It's the reverse proxy, the API gateway, from that Season 1 episode on traffic entry, only this time it stands between you and the model providers. The parts that actually touch AI, there are only 2 of them. Everything else is old craft you already know. First, think through what your app runs into when it calls those model providers' APIs directly. 1. Every single call costs real money, and you have no idea who it's being spent on. 2. The provider rate limits you, and the moment you go over, it throws a 429 back at you. 3. Every so often, it just acts up. Timeouts, errors, even a full stretch of downtime. 4. Not every question is worth the most expensive model, but if you connect directly, you can only treat them all the same. Connect directly, and you have to swallow all 4 of these yourself. The gateway exists to catch all 4 of these in one place, all at once. Because it's the one point every request has to pass through. That single pass-through position is the root of everything it can do. 4 demos, one at a time. The first one, and the star. Semantic caching. A single call to a big model isn't cheap, and in live traffic, a huge share of it is the same question worded differently. How do I reset my password and I forgot my password? Help me both want the same answer. But a traditional cache sees 2 different strings and misses outright. It barely hits any real traffic. Semantic caching takes a different approach. It turns the question into a vector, and as long as it's close enough to some earlier question, it just returns that cached answer. Sound familiar? This is the vector search from last episode, only this time what it's searching is past questions. I ran it on 400 queries.
The exact match cache, hit rate, just 16%. Because real users never repeat themselves word for word. Switch to a semantic cache, threshold set at 0.85, and the hit rate jumps to 98%, saving 98% of the spend.
But there's a weak spot here, and it's that threshold. Set it too loose and things go wrong.
Drop the threshold to 0.78, and the hit rate barely climbs, but 63 false hits show up. A refund question matched the cached answer for cancel subscription, handing the user a confident, wrong answer.
So this whole trick lives and dies by the threshold. The cache is a vector search over past questions. That threshold is the whole game. And the cache still needs some minding. Answers go stale. Stock, prices, policy. Today's answer may be wrong tomorrow, so every cache entry needs an expiry time. You can't keep handing people last year's stale answer. But even so, in real production, the share of repeats and near repeats often reaches 30 to 40%, and what you save is that 30 to 40% in cold, hard cache. The second part, semantic routing. Not every question deserves the most expensive model. What's 1 + 1, hello, for these a cheap little model is plenty. Only the genuinely hard reasoning gets the big model. The gateway takes one look at the question and routes the easy ones to the cheap model, the hard ones to the big model. It's still that reverse proxy routing from Season 1, just with a classifier added out front. I ran 400 queries, 65% easy, 35% hard.
All on the big model. Not a single one wrong, but it costs $12. All on the cheap model. Only 40 cents, but every hard one comes back wrong, and quality drops to 66%. Semantic routing. $4.60, quality 95%. At just 39% of the all big model cost.
Where does the savings come from? Because most of the traffic was easy to begin with. And the only risk is a misroute. 19 hard queries got sent to the cheap model by mistake and bombed. The more accurate the router, the more of that quality you win back. So how do you judge hard or not? The cheapest way is to take the question's embedding and compare it against a pile of examples labeled easy or hard, whichever it's closest to. That's what it is. If you want to be fancier, train a small classifier. And there's an even more robust play, called a cascade. Let the cheap model try to answer first, and if it isn't sure of itself, escalate to the big model. Letting the model raise its own hand and admit its stuck beats, guessing blindly at the door. Put plainly, it's just a load balancer. Only the key it splits traffic on is how hard is this question? The third part, rate limiting, retries, fallback. The gateway sits in front of the provider APIs, and those APIs will rate limit you with a 429, hit you with the occasional 500, and every now and then go fully down. If you connect directly, every one of these turns into an error right in front of the user. I ran 500 requests against a provider that rate limits, has a 9% chance of glitching, and goes down for a stretch in the middle.
Direct connection, the user-facing success rate is only 67%. The 429s, the 500 errors, the outage, all of it lands untouched, right in the user's face. Add the gateway. Success rate, 100%.
It uses a token bucket to throttle your calls so you never step on the provider's rate limit. When a transient error hits, it retries a few times with backoff, and most of them come back. If the primary provider goes down, it fails over to the backup. There are two more details worth mentioning here. 1, you must set a hard timeout, so a stuck request doesn't hold a connection forever. Big models often stream their output token by token, so if the first token is slow to arrive, you have to fail it fast and retry right away. 2, the backup provider you fail over to should ideally have an API and output format compatible with the primary, otherwise you switch over fine, but then the code that parses the response crashes. This is the same kit you'd add for any unreliable dependency. A rate limiter, retries, a circuit breaker, only this time aimed at the model providers. The fourth part, and the easiest to overlook, observability and cost governance. Every call costs money, and that money is scattered across a pile of teams, a pile of tenants, a pile of models. If every service connects to the provider on its own, who spent how much, you don't find out until the bill arrives at the end of the month. And by then, some runaway job has long since burned through the budget. The gateway is the one point every call passes through. Precisely because of that choke point position, it's the only place that can meter per tenant and set a budget cap for each one. I ran it with 4 tenants, one of which went runaway.
No gateway. That runaway tenant ate 84% of the spend all by itself, $13 total, on a budget of just $8, over by $5. And all of it you only discover from the invoice. With the gateway, it caps that tenant at its own $2 share and cuts it off once it goes over. The other 3 tenants aren't affected at all. Total spend stays inside the budget, and how much each tenant spent is crystal clear in real time.
And metering is only the most basic part. From the gateway's position, you can also log every request and response, so you can go back and review what answers production actually gave users, which model is slow, which one is erroring. But the moment you start logging, you run straight into privacy. A user's input may carry sensitive information, so you have to redact it first. You can't just dump it into the logs as is. It's the same idea as the agent platform's cost gate, only this time, it governs the entire fleet. The honest card. An LLM gateway, taken apart, is just this. A cache, plus a router, plus a rate limit retry fallback layer, plus a metering and observability plane. It's that API gateway, that reverse proxy, from the Season 1 episode on traffic entry, only this time it's aimed at the model providers. The parts that actually touch AI, there are only 2. The semantic cache and the semantic router both rely on embeddings. Everything else is old craft you already know. Caching, load balancing, rate limiting, circuit breaking, metering. It's the front door to the whole season. A few last pitfalls. 1, with the semantic cache's threshold, better to stay conservative. Don't gamble on serving wrong answers just to save a little more money. 2. The router's accuracy hangs directly on quality. A misrouted hard query costs the most, so it's worth watching on its own. 3. The gateway is a central point, so don't pile too much logic into it. If it slows down, every request slows with it. It should stay thin. Let's wrap up the whole season while we're at it. Across these 5 episodes, we went from RAG to the agent platform, the inference service, vector search, and finally today's gateway. Line them all up together. A request comes in through the gateway, gets cached, routed, rate limited, metered, and fans out to the inference service. The inference service feeds the model. The model drives the agent's loop. The agent grounds itself with RAG and uses the vector store as its memory. 5 AI native systems, and taken all the way down. Not one of them is magic. They're all old parts: queues, caches, indexes, rate limiters, gateways, just wearing new clothes in this new AI setting. That's Season 3. See you next season,